everyone. Welcome to Algorithm Seminar. Today we're happy to have Neel to give a talk here. He works on the mechanistic interpretability team at Google DeepMind. He previously worked with Chris Olah at Anthropic on transformer circuit Nanda, and has done independent work on reverse engineering, modular addition, and using this to understanding grokking. Please welcome our speaker.
Thanks a lot for inviting me around. I'm excited to see so much interest. So yeah, the spirit of this talk is broadly, what even is the field of mechanistic interpretability? What do I see as the areas of interesting work and frontiers there? And what kind of problems would I be excited to see people working on if anyone here is interested in getting involved? And you can see my slides at this link, and a couple of other resources I made for people interested in independently learning more about the field. So yeah, so I guess to begin, a question I imagine some of you have is, what even is mechanistic interpretability? So to me, the core hypothesis of the field is that neural networks, when trained, learn human comprehensible algorithms. These models can be understood, but by default, they have no incentive to make these algorithms legible to us. And the challenge is to learn how to make this legible. What does a rigorous science of reverse engineering these models look like, where we can actually understand the learned algorithms without tricking ourselves? There's an analogy here between this and how you might reverse engineer a compiled program binary to the underlying source code. And the claim that mechanistic understanding is possible is like kind of a bold and controversial. It's pretty standard wisdom in the field that neural networks are inscrutable piles of linear algebra that make absolutely no sense, but just work because of divine benevolence or whatever. And so first, I want to begin with a case study on this paper I was involved in called Progress Measures for Grocking via Mechanistic Interpretability, as a case study for why I believe mechanistic understanding is possible. So the setup is that we looked at how a one-layer transformer performed modular addition. And spoiler, the algorithm we found is simple enough to fit on one slide. Why did we care about modular addition? We cared about modular addition because of this phenomena of grokking, found in Power et al., where when you take certain small models and train them on certain algorithmic tasks, they will initially just memorize the training data, but then if you train them again and again for a really long time on the same data, they will seemingly just suddenly generalize. And this work was a bet that we could achieve mechanistic understanding of the algorithm learned and use this to understand why the models grokked. So how did we get any traction at all on the mysterious black box? The first hint is that there were all kinds of indications of periodic structure in the model. Here's some existing graphs from the literature of dimensionality reduction on the embeddings, where you see circles emerging. Here are heat maps of neuron activations or specific attention weights. And we see just like really weird and striking periodicity. Something here seems to be going on around that. And the key insight that really unlocks the problem is to apply the Fourier transform to the input space, where rather than thinking of it as a lookup table, rather than thinking of the embedding as a lookup table that just represents each of the possible inputs, we instead think of it as converting each input to a linear combination of sine and cosine waves of different frequencies. And if you look at the magnitude of each of these waves, we see that it's incredibly sparse. For comparison, here is it an initialization. And with this insight, we were able to do a bunch of further work and understand the learned algorithm. At a high level, the idea of this algorithm is that modular addition is equivalent to composing rotations around the unit circle. Composition adds the angles, and because they're rotations, you get modularity for free. And you can look inside the model and see things like the embedding is about translating the inputs to these sine and cosine waves of different frequencies. The nonlinearities, the MLP activations, and the attention softmaxes use trig entities to compute the composition, represented as sine and cosines of A plus B. And the linear map from neurons to the output logits use further trig entities to get cos of A plus B minus C, where C is each output logit. And the final softmax is used as essentially an argmax. Cosine is maximized at 0, and A plus B minus C is 0 when C is A plus B. And because cos is periodic, you get mod n for free. And I did not go into this expecting to find this out. I just found this by staring at the weights and doing a bunch of exploratory reverse engineering. So claiming that I actually understand that algorithm is kind of a bold claim. So why do I believe this? We presented 4 lines of evidence in the paper. The first I've already covered, the surprising periodicity. The second is that we can just mechanistically read off certain steps of the algorithm from the model weights. Certain neurons correspond to frequency 14. And when we look at these neurons and their output weights from there to the logits, we see that it's basically entirely frequency 14 terms, the things we predict from this trig entity. The next line of evidence is that we can zoom in and approximate the neurons. The algorithm predicts the neurons will have a specific form. And it turns out that if you take this and a couple of other terms, you can approximate the neural activations incredibly well. Where, for context, this is a rank 6 approximation of the neurons in a 12,000 dimensional space. And finally, we can verify that we've correctly understood it by doing ablations. If we ablate any of the bits our algorithm says should matter, performance tanks. But if you ablate everything except for the algorithm says should matter, performance actually slightly improves. And so those are a bunch of arguments for why this is really the algorithm learned by the model. But is this useful? Can mechanistic understanding teach us real things about models, like why they grok? I sure hope so. So just before I try to give my answer to this, I kind of just want to remind people who might have seen this work or seen grokking before that grokking is really weird. Like, naively, you train a model, it memorizes or it generalizes, and it just stays there. But this switch is just bizarre. And I kind of want to just invite people in the audience to just take a moment to think about why they think models grok. Here's a selection of ideas from literature. Great. After that tactical break to soothe my throat. So what I found when I looked inside is that, Rena?
Yeah, so I thought even models that memorize do generalize, even if they're very big.
Sorry, can you repeat the question?
So I thought models that are large and memorize, they also have the ability to generalize.
Yes. So a model which, so I would count a model which has good test loss and better train loss as one which is kind of both generalizing and memorizing. But to me, the thing which is striking about grokking is that it switches. Like, I think if you observed that in a language model, it would be like at least somewhat surprising.
So you're saying grokking is the case where it does memorize, but it does not generalize? Is that has that been seen a lot?
I'm saying that grokking is when it initially memorizes and does not generalize, but then after a long time, there is a sudden dramatic convergence.
Okay.
And it's that specific sequence of events. Okay. Any one component of this is not super interesting in isolation. Though I do think the sudden generalization is the most, even without the divergence, just the sudden test drop at some point is pretty interesting in general, which I'll get to a bit more later on. But all right, so why does grokking happen? So with this understanding of the circuit, we can just look inside the model as it's trained. And we see that initialization, it doesn't really know anything about the frequencies. But then during this seeming plateau, where it's much worse than random, we see that the embedding is becoming incredibly sparse. And my interpretation of this is there are 3 phases of training. The first is memorization, up to here, where the model just memorizes training data. It doesn't know anything about Fourier terms. Then during this seeming plateau, I call this circuit formation, where it's steadily interpolating from the memorizing circuit to the generalizing circuit, while somehow preserving train performance throughout. Why does test loss remain worse than random, even though it's already learned so much of the right solution? Because if you're generalizing and memorizing, because memorization does so badly out of distribution, this means that your overall log loss is still pretty poor. And so why do we see this sudden generalization? It's because when the model has transitioned far enough towards the Fourier solution, it no longer needs the parameters spent on memorization. And because we're using weight decay, other forms of regularization also work, the model can now clean up the weight spent on memorization. And that's what leads to this drop. Grocking is not plateau followed by sudden generalization. It's gradual generalization followed by sudden forgetting of the alternate poorly generalizing solution. And that was a bit in the weeds. But the key takeaways I want to draw your attention to from this section are, firstly, that a mechanistic understanding is useful. It can help us understand confusing mysteries that many other people have tried to solve. But more importantly, mechanistic understanding is actually possible. We can take tasks that were not selected to be interpretable, and we can go and reverse engineer them and discover beautiful emergent structure. And I think a pretty cool line of research is taking more algorithmic problems like these and trying to see what beautiful structure is beneath. But all right, so zooming out a bit, I want to dig more into what I mean by mechanistic interpretability. So, as I've said, it's based on this hypothesis that models learn genuinely human comprehensible algorithms and can be understood. And the way we normally break this down into 2 concepts, features and circuits. Features are properties of the input represented with activations inside the model, which you can think of as variables in the computer program. And circuits are the algorithms that take these features, these properties of the input, and use them to compute more complex features. Here's a cute microcosm of a circuit. We have neurons detecting features like car windows, car bodies, and car wheels, and a convolutional kernel that connects them up to represent a car. Because if you've got windows on the top, body and wheels on the bottom, you're probably a car. And mechanistic interpretability thus far has often looked at fairly narrow questions like, how does modular addition work? What's up with specific neurons? To me, what I see as the dream and purpose of the field is as forming a foundation for a rigorous science of interpretability. There's this whole college industry of papers about how traditional forms of explainability and interpretability are subtly flawed or illusory. And this is just because interpretability is incredibly hot. And to me, the way we form a true science of interpretability is by taking narrow questions that we can really reverse engineer and understand in detail, and using our insights from this to find things that are less rigorous and more scalable, but which we can validate in the settings we really understand. A deeper reason with my Google DeepMind hat on for why I think mechanistic interpretability, or any kind of rigorous deep interpretability, is important, is that I really want to understand the internal cognition in a model. And the reason I think this is really important is that I want to know whether we can distinguish between a model that is genuinely aligned with us or one that's just telling us what we want to hear. And I think that most machine learning purely concerns itself with the inputs and outputs of a model. But I think that in the world of foundation models, of GPT-4, Gemini, whatever else is next, this is just not enough. Here's a particularly evocative example of GPT-4 being asked to convince a TaskRubber worker to perform a capture for it. It asked a question, GPT-4 realized instrumentally that it should lie, and it made up this fairly convincing lie that has a vision impairment. And, you know, we can literally see GPT-4's thoughts. So I'm not that concerned about GPT-4 causing an existential catastrophe. But to me, this is a microcosm of the kind of problems I'm afraid we'll have in the future as we get closer to genuinely capable and general systems. And a concrete world that I'm pretty concerned about is that Google DeepMind succeeds. We make AGI. We have no idea how it works, but it looks aligned. We try to trick it, we try to probe it, and it just seems to be nice and do what we want. And I feel pretty concerned about this world because if a system is sufficiently capable, it's incentivized to look reasonable and good and aligned, because all of our current training methods are purely about the outputs of the system and what we can measure, which means that any system has an incentive to tell us what we want to hear. But we don't know how to measure the internal cognition unless we don't know how to distinguish between the aligned solution and the sycophantic or deceptive solution. And I broadly think that just any kind of good interpretability seems really useful here. One angle I'm particularly excited about is the idea of eliciting latent knowledge, understanding what internal beliefs the model has by doing interpretability to it, rather than purely looking at the model's outputs and asking it questions. And I don't know, this is my personal motivation. There's a lot of other reasons you might care about mechanistic interpretability, nearer term things, the fact that it's just incredibly beautiful and pretty, but this is like what I'm personally coming from. One of the unique things I think it has the potential to add. Any questions on either of the sections so far before I move on to the next one? Feel free to just unmute and interrupt. Cool. All right. So I want to dig a bit more into this idea of a circuit, how the model thinks. So in this paper, El-Haj et al. That I was involved with, we found this circuit that we call an induction head in two-layer attention-only language models, transformers. So the idea of an induction head is that language often contains repeated text. If you see the word Neel and you want to know what comes next, unfortunately, Nanda is not necessarily the best guess. There's like lots of other things that could come next. But if you look at the previous text and you see Neel Nanda has occurred 5 times, Nanda is a lot more likely to come next. And so the ability to detect and continue repeated text is like an important thing for a model to learn. And importantly, it's not something you can purely do with like n-grams and surface level statistics. It's something that you need an actual inference time algorithm to notice, because you need to search the context for whether the current thing has come up before and look at what came after it. And we found this algorithm where 2 attention heads work together to do this. The first one, for each token, looks at what came before it and writes some metadata. So like for the struction token, it writes node was the token before me. And then the second head, the induction head, looks at each token and looks for where their metadata says the thing before them was equal to the token it's starting at. It looks for tokens whose metadata says the thing before me is node. Then the induction head looks here and says, okay, that token is struction, I'm going to predict that comes next. And the exact details aren't super important to follow, though we formed a pretty good mechanistic understanding of at least the simplest form of this that you can see in this great blog post. But this turned out to actually be a really interesting result. So first off, we found induction heads in basically every model we've looked at. I recently found them in Chinchilla 70 billion. And a deeper reason they're interesting for people who don't care about interpretability is the case study of emergence and in-context learning, which we studied in a follow-up paper, also now. So in-context learning is one of the more fascinating things that modern language models can do, where they are able to track long-range dependencies in the text, use what comes before to become better at what comes next. Some of the more famous examples are things like few-shot learning, where seemingly giving a model examples of a task can make it, I don't know, possibly learn how to do the task. Their interpretations wildly vary. And more generally, it's kind of surprising that models can use text that's, say, several pages back in order to productively predict what comes next. If I was trying to code a basic language model, I don't really know how I would tell it to do that very well. And a surprising fact about in-context learning is that it's emergent over training. If you operationalize it as better average loss on late tokens rather than early tokens, there's like a narrow band of training where the model goes from not very good at it to about as good as it's ever going to get. And this is pretty surprising. You'll also note that it only happens in models with 2 layers or above, though it also happens in up to 13 billion parameter transformers, as we studied in the paper. And the striking thing is that this exactly coincides with the emergence of induction heads that also seem to form very suddenly in the same period. And in the paper, we argue that induction heads are an important part of how the model does in-context learning, and present a bunch of further reasons why we believe there's a genuine causal link here, rather than just a hidden variable explaining the correlation. Like if you make a minimal architecture change so one-layer models can form induction heads, one-layer models can now do much better in-context learning and have the same emergence that corresponds to the formation of the heads. And so, in summary, the takeaways I want you to have from this section are that, at least in certain cases, models learn legible algorithms called circuits that can be understood. We can reverse engineer these algorithms, and these are deeply tied to phenomena that non-interpretability people care about, like emergence and in-context learning. And I think 2 areas of future work I'm pretty excited to see here. One is looking more into toy language models. We found induction heads by looking at 2-layer attention-only language models. These are like a much simpler and more tractable setting, but turned out to give us deep insights about much broader settings. And secondly, doing more interpretability on training dynamics. Emergence during training is a pretty interesting phenomenon. And to me, this work is very suggestive that trying to understand what circuits are behind various kinds of phase transitions and emergence might help us get a much better understanding of why this happens, predicting when this might happen, and various other questions of that form. Any questions on that? Cool. All right. Feel free to also just put questions in the chat throughout, and I'll either address them in a minute or whenever there's a next natural break. Okay, so how do models represent their thoughts? So, in my opinion, this section is one of the big frontiers of current open problems and exciting work in the field. So, one of the sub-goals that you need to do if you want to reverse engineer a model is to be able to decompose it to independently meaningful and composable units. Things that have, which are some interpretable property of the input that correspond to different bits of the model, such that you can analyze them individually. Because models are such high-dimensional objects, like up to like trillions of parameters nowadays, if you believe the rumors about GPT-4. This means that we just can't understand a trillion-dimensional object. But if we can find a decomposition such that into units that can be understood in isolation, then we can start to piece this together to an understanding of the whole system. And so the natural question is, how do you do this? Is this even possible? And one of the early hopes in the field was that neurons would correspond to features. And this is more reasonable than it might sound at first. So the intuition here is that models act as feature extractors. They extract different properties of the input and represent them internally. And even if two features are correlated, you want to be able to represent them independently in order to do this computation. For example, this is a picture of a canine and this is a picture of a pet features are clearly correlated because dogs. You want to have separate processing for this is a pet and for this is a canine. And if two features share a neuron, because nonlinearities act element-wise, they act on each axis in turn. If two features share the same axis, then the effect on the model from changing one feature will depend on the value of the second feature. While if each feature corresponds to separate neurons, then this just works great. And so this is like a beautiful theoretical argument for why neurons would correspond to features. Sadly, it's bullshit because of this phenomena of polysemanticity. So it is just empirically the case that often when you look at neurons, they seem to represent multiple unrelated things. Here's an example of a neuron from Go et al. In Clip, which represents both poetry and also poker and games. And so this is kind of surprising. The argument for why models should want to have meaningful neurons all seems pretty legit to me. So why does this happen? The hypothesis is superposition. So we have the behavioral observation that neurons act on all things. Why does this happen? The hypothesis is that models want to represent more features than they have neurons, because the more features you have, the more you can reduce the loss. And the hypothesis is that models learn to simulate a much larger and sparser model and compress it into the lower dimensional space of the actual model using clever compression schemes. And if a model is willing to deal with the resulting interference, this can allow it to represent many more features in a way that gets better performance. And so the first approach here is just, does this happen? How can we think about it? Can this even happen in toy models? What is the right way to think about this kind of weird, confusing concept? And there's this really great paper, El-Haj et al., Toy Models of Superposition, which builds a toy model which has more features than it has dimensions, and tries to train it as an autoencoder to compress in features into this lower dimensional space. And they find a lot of fascinating results. It's a great page, just go read it. But most strikingly, they find that the model does learn to use superposition, but it learns to use it only if the features are rare. If the features are only there, say, 90% of the time, the model will learn to form beautiful geometric structures, like embedding them as the vertices of a regular pentagon. While if they're always there, it will just learn two features and call it a day. And I think this is really exciting work. And the reason I found this paper really exciting is that even though it was just on a toy model, it helped build intuitions and frameworks for how to think about this. And a challenge to anyone who's interested in this kind of toy models work is, so there's two different kinds of superposition. There's representational superposition, where a model just has more features than it can fit in. Like it has 50,000 tokens, but only 1,000 embedding dimensions. How can it compress in these features in a way that's recoverable? Which is what this paper studied. But there's also the phenomena of computational superposition, or neuron superposition, where it has a nonlinear layer where it computes more features than it has dimensions. And the paper very briefly studied this, but I think we're still very confused about it. A toy model I'd love to see someone study is you have a model with n sparse binary inputs that are on or off, and n choose 2 outputs for xi and xj. And seeing how the model does this and how many neurons it needs to be able to do this kind of thing well. And yeah, there's all kinds of beautiful stuff that emerges when you look into this. Like, they find that if you give the model more dimensions and a bunch more features and vary the sparsity, it actually spontaneously specializes into different geometric subspaces. So for example, this is a single model, and some of its features have formed triangles, where there's 3 features in a 2-dimensional subspace, and every subspace is orthogonal to every other subspace. And some features have paired up into antipodal pairs, where you've got 2 features in the same dimension. And that more broadly, if you measure the fraction of a dimension taken up by a feature, they form these discrete energy levels. And I don't really know why this happens. I'd love to understand why, but it's also just really beautiful that this kind of thing emerges from such a simple toy model. And yeah, there's a question of what can you do about this? And one of the approaches that seems the most promising here to me is the idea of extracting features from superposition. We have this compressed space that has more meaningful directions than it has dimensions. And what we want to do is be able to find these meaningful directions and to be able to take any actual input and understand how it is a linear combination of these meaningful directions. And as you may have noticed, the problem of finding n meaningful directions in a space with fewer than n dimensions is underdetermined, because it's not linearly dependent. It's not linearly independent. The key trick is that we should expect these meaningful directions to be sparse, because the model, any given input doesn't have most features. Most text is not about the Eiffel Tower, and the Eiffel Tower direction will not need to activate. And there's all kinds of fields around neuroscience and compressed sensing about how to find these kind of sparse bases and models. And I think a really exciting direction is trying to do this to real models, or even to toy models, and seeing how far you can take it. So something which is a bit unsatisfying about what I've covered so far in this section is that it's very much focused on toy models. It's very much focused on kind of theoretical ideas of superposition. And it's easy for this kind of theory to drift apart from what actually happens in practice. And another more empirical or biological direction is studying superposition in the wild, trying to understand whether this actually does happen, and validating our intuitions, figuring out whether this is why polysemanticity actually arises, and whether this is as big of a block on understanding models as I believe it is. And in this paper from one of my mentees, Wes Gurney, we looked into which neurons were used for different tasks. And one case study was how models detect compound words like social security. We find that models have many mediocre social security detecting neurons. Things like this, that are doing it systematically, but are not very good at it. Definitely you could not cleanly disentangle social security from everything else, just because there is so much everything else. Note the log scale on the y-axis. But if you add together the activations of these 3 neurons, you suddenly get a very good social security detector. And to me, this is pretty strong evidence that the model is usefully representing this as multiple neurons in a distributed form. Why do I think this is superposition rather than just a non-neural aligned feature? because there's just so many compound words and multi-token words that a model wants to represent, and so few neurons. And in practice, models seem to be able to competently deal with these compound words and their meaning. But it just seems pretty intuitive to me that models are going to be using compression schemes and superposition in order to do this. And an open question is just further investigating whether superposition happens in practice and where. For example, we found that these 3 neurons represented social security. But we didn't find out if this is like all of the representation. Is it more like 3 neurons or is it more like 100? I have no idea. Another challenge is, do there exist any meaningful neurons at the opposite extreme from being skeptical of superposition? Does it ever not happen? Another thing we found in Gurney et al. Is the French neuron. This neuron that just seems to very strongly activate for any token in French text, and basically not activate at all for any token in non-French text. And I love this graph so much. And but I claim that we've not actually shown this is a mono-semantic neuron. We haven't looked at the model's full pre-training distribution. We haven't falsified the hypothesis that it's polysemantic, but the other feature is really rare. It does still overlap a bit. Is that fine? Is that not fine? More broadly, what does it even mean for a token to be in French? This activates on text like sacre bleu or très bien in English text. Is that fine? Is that bad? I don't really know. I think that a project that was just trying to figure out whether this kind of thing is really monosemantic, what do rigorous standards of proof for a question like this look like, feels super interesting to me. In the curved circuits paper from Camarada et al., they do what I consider to be one of the gold standard investigations of meaningful neurons, looking at how an image classification model detects curves that I think might be useful inspiration. Okay, so that's the section on superposition and how models represent their thoughts. Any questions on that section before I move on? All right. I will interpret this as either I'm explaining things perfectly or terribly. I'm not in the middle. All right. So next section, building scalable techniques. What does it look like to really understand and reverse engineer a model at larger scale rather than the incredibly toy things done so far? So one of the more exciting areas that gives me optimism about this kind of work scaling in the last couple of years has been refining ideas around causal interventions. So causal interventions, where you just intervene on a model's internals, are a thing people have been doing forever in interpretability. Like you delete a neuron, or ablate the neuron, and you see what happens. And the naive hypothesis is that if you get rid of it and nothing changes, it doesn't matter. And if you get rid of it and things do change, then it was important for this task. And the problem with ablations is that often we want to answer much more precise questions about a model than just, does this bit matter? And ablations are just not surgical enough. They can't distinguish between things like, this was a bias term that most things in the model need, or this is very specific to the task. And the idea of activation patching is to be much more surgical. So let's say we want to understand how the model does factual recall. How does it know the Big Bang Theory premieres on CBS rather than any other network? So the model is actually going to be using a bunch of different circuits on this task. It's going to be recognizing the compound word of the Big Bang Theory. It's going to be realizing it should do factual knowledge recall. It's going to be looking up information about the Big Bang Theory. It's going to be realizing it should be looking for a TV network. It's going to be realizing this is in English. I should do English-y things. And The idea of activation patching is that you have two forward passes of the model, one on the clean input, the Big Bang Theory premieres in, and one on a corrupted input where you remove some key information, like you add Gaussian noise to the subject, or you replace it with the name of another TV show, with the goal being that these two runs differ in only the detail of what the subject of the sentence is, so them to capture the bit of the model that looks up which network the Big Bang Theory is played on. And you then intervene on the corrupted run by replacing a specific activation with its value on the clean run. And you look at how much this fixes the output from the corrupted output to the original clean run. And if this works, then we know that, okay, this must have contained like sufficient information to represent the Big Bang Theory. And I find this kind of thing really striking evidence. And in practice, it often looks incredibly sparse. Like, rather than most things mattering, it's like, okay, these layers on the theory token matter, these attention heads on the on token matter, maybe a couple of LP layers matter, but like most don't. And I think there's a lot of interesting work to be done trying to refine and make more rigorous the techniques. The literature is full of all kinds of different approaches and ideas, and there's all kinds of subtle details that really matter. Like if you use accuracy or probability as your metric, your results can be much more misleading than if you use softer and more continuous metrics like logprop or logits. And I would love to see someone trying to tackle the question of what would a textbook or tutorial in principled approaches to causal interventions for interpretability look like. A case study of applying these interventions is Wang et al., the interpretability in the wild paper. So they tried to understand how models could do indirect object identification, how it could take prompts like when John and Mary went to the store, John gave the bag to, and complete it with Mary rather than John. And this is actually a non-trivial task for a model to do, because understanding you should predict one of these names is not that hard. But understanding that you should not predict the one that was repeated here, but instead predict the other one, is actually kind of non-trivial. And they found this 25-head circuit inside GPT-2 small that was responsible for this task, that roughly clusters into heads that detect that John was repeated, heads that move this information to the final token, and heads that copy all non-repeated names to the output and then predict them. And okay, so I don't intrinsically care about this grammatical task. So the actual question is, why is this interesting? So one reason I'm really excited to have case studies of genuinely understanding a circuit in a model is I think these can help us validate and benchmark in interpretability techniques. One of the more fascinating and surprising findings of the paper is that of backup heads. So backup heads are a phenomena of self-repair in the model. There's a forthcoming Google DeepMind paper from Tom McGrath exploring this in more detail. But the core idea is, when you delete a core head in the model that you can see just directly impacts the output, even without anything else, other bits of the model will shift their behavior to compensate for the ablation of that head. This means that when you just ablate it and look at the effect on the output, without really engaging further with model internals, this can actually be incredibly misleading. Here's a scatter plot of the original direct effect of each head and the post-ablation direct effect of each head. The original head goes from important to nothing, obviously, but then we see a couple of other heads like move significantly off diagonal because they are compensating, including this one head that significantly negatively affects the correct output in a way that is kind of fascinating and surprising. And to me, this kind of observation is really important and validates this desire for depth over breadth, because this is the kind of interpretability illusion. It's so easy to miss because you delete a thing, it doesn't make sense, so it doesn't matter, is just like such a compelling hypothesis. Daniel asks, do we have evidence if this is due to dropout? So we know this occurs in models without dropout. We also know this occurs more in models with dropouts. We don't know why this occurs in models without dropout. We also don't know if GPT-2 was trained with dropouts, because apparently OpenAI lost the code and forgot to mention this in the paper. As I discovered from asking a friend on the OpenAI interpretability team. This was in GPT-2 small. We don't know why this happens, which is another fascinating open question. Since, like, what? Why would this matter? My two guesses are that the model is doing some superposition with attention heads, where some head means several different things, and if the head gets interrupted because its other task also came up, then another head learns to take over. Or because there's just like a bunch of kind of jitter during training, where like grain and send, incredibly noisy, Atom is even messier, it just like jostles a circuit, and the model wants to recover the loss, so it like is incentivized to have things that prevent that happening. Are the two most compelling hypotheses I've heard. But I kind of just view this as a fascinating mystery about models. It's a big open question. And I have a tutorial in PyTorch where I speed run replicating the basic analysis of this paper. I think that a pretty cool direction is doing this kind of thing in more detail, doing this kind of thing on just more tasks models are capable of. Like, models can count. GPT-J can do addition. And I recently poked around and found things like a neuron that activates if the output ends in a 7, or if both inputs are multiples of 3. What's going on with these circuits, and what can they tell us about underlying principles of models in general? We can also scale even further. In Conley et al., they just took the basic ideas of interpretability in the wild and just did them automatically. And they found that they could mostly automatically recover the indirect object identification circuit. And there's a bunch of other ideas for how you might do automated like what are other directions for automated interpretability. What I'm particularly excited about is automatically discovering features in a model. One of the core problems of classical interpretability of things like probing is that they implicitly assume what features are going to be there. They implicitly assume that we know what we're going to go find. And I think one of the major promises of the depth-first mech-interp approach is that we can be surprised by the features we find. Just how I did not expect to find that modular addition was done by Fourier transforms of all things. There's a recent OpenAI paper using GPT-4 to explain GPT-2's neurons that I think is a compelling proof of concept for this kind of thing. Yeah, that was a long, wide-ranging section. A couple of takeaways. Looking for circuits in the wild, in real language models, is pretty doable and pretty interesting. Having more case studies like this that we actually understand can help us validate more scalable techniques. I'd say we currently have maybe like 4 such case studies of varying degrees of well understood. It seems kind of embarrassing we don't have at least like 20. And more broadly, causal interventions, and in particular, interventions that are about resampling and activation from another run, are really important techniques for understanding models. And I have posts giving a bunch of open problem ideas for both finding more circuits in these models, and also for what better techniques or tools might look like. Any questions on that section? All right. So, final case study. Emergent world representations in Othello. So, in this great paper, Lee et al., that I'm sure some of you will have heard about, they trained a language model to play the board game of Othello. They gave it a synthetic dataset of randomly generated legal moves and just trained a GPT-2 model to predict the next from scratch, not pre-trained. And the really surprising thing they found is this emergent world representation. They found that you could probe the model and on each position recover a model of the board, of like the state of the board and what was on each cell. And that not only could you recover it, but that you could causally intervene on it. And if you causally intervened, the model would make legal moves in the new board. And this is surprising because the model only ever sees the moves in like chess notation. Like I put a piece on cell D6. It never even realizes there's a board. You just give it like abstract sequences. And this is just kind of wild. And it was a very popular paper. It was an oral at ICLR. But the thing which was striking to me about this is that their techniques were just very powerful. They couldn't find it with linear probes. They could only find it with nonlinear probes. And the way they causally intervened is they did gradient descent on the model so that the internal activations in the residual stream were put through the probe and output this different board state. And gradient descent and nonlinearities are both like sophisticated techniques that I think can often do a bunch of computation in a way that can mislead you about the underlying results. In particular, a common hypothesis in mechanistic interpretability is the linear representation hypothesis, made most famous by the Word to Vec paper. That models represent different features of the input as directions in space that add together. For example, man minus woman is king minus queen. There's a royalty direction and a gender direction, and each of these nouns is made up out of a linear combination of the two. Or there's a walking versus swimming and a like tense direction for verbs. And to me, this hypothesis is interesting, both because it's a pretty strong claim about models. It's really convenient. It's not like fully validated, but it's like a strong hypothesis that bears out in the case studies we've looked at so far that makes real claims about models and can be falsified. And the Othello work seemed like actually pretty strong evidence against. Linear probes failed, nonlinear probes worked, and the probes were so legit, you could use them to edit what the model thought. And despite the board state having no direct connection to the outputs, this changed the model's outputs. And what I found in some follow-up work is that the previous work had found some mild illusion. Rather than the model learning to compute whether the cell is black versus white, the model learned to compute whether it had the color of the current player or the color of the current opponent. You can train a linear probe for near perfect accuracy when you realize that you need to switch the labels every move. The probe just gives the correct answer, but it switches colors every time. And because the model is trained to play both black and white moves, from its perspective, this is just far more natural. Like, it doesn't see colors on the board. It purely wants whatever has the best predictive power for the task we've given it. And to me, this is both a fascinating case study of mechanistic analysis winning out. I found this by just spending a weekend doing a bunch of narrow investigation of specific circuits. And because it shows that there are real underlying principles and hypotheses about models that can generalize, survive falsification, and tell us things about future models. And to me, this further validates the depth-first approach. And I have a bunch of posts about my follow-up work here and future direction I'd love to see building it. And yeah, I will end here. You can find my slides at this link, and hopefully we'll email them around. If you're interested in learning more, I have a guide on how to learn more about the field, an explainer where I try to define a bunch of key terms in the field, because God knows we have more jargon than we need. Library in PyTorch. I don't know if people here are able to use PyTorch because Google free, which to better enable mechanistic interpretability, and a sequence called 200 concrete different problems in Mech Interp, giving a bunch of ideas for concrete problems in this area. And yeah, thanks a lot for the interest.